Okay, so good morning, everyone. So again, that concept of the moment, okay? The moment is the ability or the measure of the ability to rotate or twist something about a point, okay? Or about an axis. So this is what we did in the last time, okay? The ability to rotate something about an axis, not a point, okay? Now, let's extend this to something more than a moment, okay? Just a moment. There is something called a moment of a couple, okay? So let's see here what's meant by couple and what's the moment of it and how to calculate it about any point. Let's see this, okay? So moment of a couple. So before I do this, just a quick note here. For the lecture notes, okay, I use some like color, here, usually I use black. If you realize this, I use black for like theory that we mention, okay? Any theory, any rule, anything that is not an example, okay? And then I use red for the heading of the example, okay? And blue for the solution of the example, okay? So anything in blue, that's a solution. That's not going to be part of the problem itself. Red or, usually red is the heading of or the statement of the question itself, okay? Just, that might, help you when studying. Like, for example, here, this is not part of the example, but this is a rule or something that I want you to know that, to use outside this example, okay? So, moment of a couple, okay? So what is a couple? So a definition, we have a new word here, couple. A couple is a set of two parallel forces. They have to be parallel. This is the definition, okay? Equal in magnitude. They have to be equal in magnitude, by definition. And opposite in direction. Separated by perpendicular distance to their lines of action. If we have this definition, this is called a couple, okay? So let's see this, okay? If I have a force like this and a force like this, can I call this a couple? No. What about a force like this and a force like this? Can I call this a couple? No. Why? Because their line of action, okay? There is no perpendicular distance between their lines of action, so this is not a couple. So to have a couple, I need to have one force like this and another force like this. They are equal. If this is F, this is F in the opposite direction. They have to have the same magnitude in opposite direction, parallel to each other. And they have to be, their lines of actions have to be separated by a perpendicular distance. If this happened, then I can call those two forces, okay, a couple, okay? So now, if I have this distance, let's call this distance D. So the forces are F and the distance here is d, okay, the perpendicular distance. So now, those two forces, they would have a moment, right? So let's try to take the moment of those forces about some arbitrary point, okay? Some point here. Let's call this point here O, okay? So now, before finding the moment, okay, let's find the resultant of them, okay? Those two forces, what's the resultant force of them? The resultant force. How much is the resultant force of those two forces? They are equal in magnitude, opposite in direction. So the resultant is how much? 0. 0. So the resultant force is F minus F, it's 0. As if there is no force applied. Okay? The resultant force is 0. You didn't apply any force. Applying two forces equal and opposite, as if you're not applying any force. Okay? So when you have let's say an object and you apply two forces equal and opposite in magnitude, okay? You're not applying any force. The force is the type of interaction. It's a linear type of interaction. So applying two forces equal in magnitude and opposite in direction will not make this object move linearly. Okay? Will it make it rotate? Yes, it will rotate. That means that those two, okay, have a moment. It's like the wheel here, driving wheel. When you're driving, you apply a couple. You apply two forces equal in magnitude and opposite in direction. You definitely don't move the wheel from its location, okay, but you're rotating it, okay? You have the ability. Applying a couple will be able to rotate the wheel, okay? So now, let's see the resultant moment. They have, it appears, it's clear that there is a resultant moment, right? But let's try to find how much is that resultant moment. We mentioned before, when we talk about moment, okay, I cannot just say moment and that's it. I have to say, find the moment about a point, okay? So which point? Let's say we want to find the moment of those two forces about this point O, okay? Let's find it, find the moment about some point O. So how to find the moment about point O? The vector of the moment. What's the vector of the moment?
The distance multiplied by
R multiplied by F, right? But here we have two forces. So I have to find this moment, the moment of each of those forces, and add them together, right? So now I have to have, let's say, from point O to, let's say, this point, let's call it point A. So I need to have RA. And then from this point to any point here, B, along the line of action of this force, okay? And that's RB. So I have to find the moment of each of those forces. So I have to multiply here, RA, cross product, this force F, okay? Plus RB, the position vector is measured from the origin or the point that you're taking moment about to the any point along the line of action of the force, okay? Multiplied by F, right? F, the vector F. Everyone agree? Anything that's wrong here?
Since one of the forces is in the opposite direction, so why we didn't say it's negative?
Yes. So that's why I was asking this. So if this is F, then this one has to be negative F, because they are opposite in direction. Right? So now, let's, as you see here, you have R multiplied by F, and here R multiplied by F. So let's write this like this. RA cross F minus RB cross F. And then let's take F as a common factor. So here we have RA minus RB cross F. Right? What's RA minus RB?
It's RBA.
RBA. It's the position vector from point B to point A. It's this vector. RBA. Okay? Times F. Or cross product the vector F. Okay? So now that means that the moment is what? We have RBA, this vector RBA, multiplied by the vector F. Which one is F? This one is F and this one is negative F, right? So from here to here, as if you're taking moment about this point, right? This vector multiplied by this force, right? It has nothing to do with point O. It ended to be like taking moment about one of the two forces, right? So what's the direction of that moment? The direction of the moment is perpendicular to the plane, including the distance and the force, okay? So that's the direction here. Let's draw this. So the direction here is perpendicular to the plane, including the force and the distance. If F and R are in the XY plane, then it's the Z. But if it's any plane, it's just perpendicular to that plane, including R and F, okay? And the moment is the moment that we're looking for, okay? It's perpendicular to the plane, including both R and F. So now, let's write some conclusions. What did we get from what we did right now? Okay? The equation that we just found now, okay? We found that M, the moment of that couple, okay, is RBA times F. So what does this equation tell us? Can we conclude anything from this equation? Yes. We can conclude the following. The first thing is the moment of the couple about any point is constant. Why? Because it didn't depend on the coordinates of point O. You understand what I'm saying here? We took moment about point O, right? If point O was here, still it was going to be RBA times F, right? It's not going to be something different. Although the point changed, right? Because as you see, it's going to always be the distance RA from that point, okay, to F plus RB times negative F. So it only depends on RBA times F. It has nothing to do with the location of point O. Okay? So it's constant. So I really, for a couple, I don't care about the point. We said moment. When I say moment, okay? What point, right? Moment about what point. But for a couple, it's the same. I don't care what point it is. Okay? It's always going to be the same magnitude. Okay? So that's the first conclusion, first important conclusion. For the couple, the moment is constant. It has nothing to do with what point. Okay? The second thing here, the moment of the couple is always perpendicular to the plane containing the two couple forces, right? It's always RBA times F. RBA times F, okay? The direction will be perpendicular to that plane. That plane includes F and negative F. So it's always perpendicular to that direction, okay? Whatever the point you're taking the moment about, it's always in that direction, okay? And the third conclusion, it's so clear here from the equation that we had here. The moment of the couple is RBA times F, right? RBA, cross product F. So that means that the magnitude of the couple, of the moment of the couple, is equal to the magnitude of the force multiplied by the distance, okay? So it's equal to the magnitude of the force multiplied by the separating distance between the two forces. Okay? So if you would like to find the moment of the couple then, okay, the conclusion from the equation that we wrote here, we can simply state that M, the moment of a couple, is equal to R cross product F. Okay? So if I have a force F, I just pick any 2 points here along the line of action of those two forces, and that's the position vector. Okay? R. So now, the thing is, if I write this equation, M is equal to R cross product F, okay? Which R and which F? What's this? Here we have, this force is F. This force is negative F. So which one? If you use this one, it's positive. This one is, you're going to have a negative answer, right? But no. I really don't care which F you use, because with the F that you're going to use a different R, okay? So for example, if you use here, if you take moment about this point, okay, you're going to use this R and this F. Or I can take moment here, so I'm going to use this R, which is negative R, times the negative F. So I really don't care which F and which R you use, as long as you use the correct set of R and F. Okay? So let's say here this is point B, this is point A, okay? A and B. So here the question is which R and F to use to answer this question, any set you choose. Like for example, if I take moment about point A, okay, then it's going to be from A to B. So R A to B, from A here to B, and then I'm going to multiply this by negative F. Okay? Or if I take moment about point B, it's going to be R B A cross product F. Right? Are those equal to each other? Yes. RBA is negative RAB. So they are the same. Whether you use this one or this one, it's the same. This is the proof here. Okay? So you can use any distance, any R. If I take R from here to here, I'll use this step. If I take R from here to here, I'm going to use this step. That's it. Okay? You can use whatever you want. Any question here? Okay, great. So that's the couple, okay? The moment of the couple. So again, the most important thing that I want you to understand here, the moment of a couple, okay? Does it relate to a point? No. The moment of a couple is the moment of a couple. About point A, B, C, D, any point, it's the same magnitude. Its direction is constant. It's perpendicular to the plane, including the two forces. That's it, okay? So now, let's solve some examples. So example 410. So in example 410, it's a two-dimensional problem, okay? We have an object, it looks like this. It's in the X, Y plane, okay? So all the forces that we're going to draw now, all the dimensions is in the X, Y plane. So any moment will be in what direction? Z, okay? Rotation about Z. This object, there are some forces applied on it, okay? What are those forces? Let's draw this in purple here. We have a force here, a vertical force, F1, equal to 200 pounds. And a force here, F1, equal to 200 pounds as well, but downwards. Here at point B, let's call this point B. So the points here, this is point A, B, okay? At point B, we have a force F3, inclined force of 300 pounds. And here at this point, there is a parallel and equal force F3 of 300 pounds. Okay? Let me try to draw this to be parallel. Okay? And then we have a force here. Third force, F3, sorry, F2. That is equal to 450 pounds. And another force here, equal and opposite, 450 pounds. What's the dimensions given here? We have a set of dimensions. This distance, d1, it's 4 feet. This distance here, these two forces are perpendicular to that side, and this distance here of this side is 5 feet. We're going to call this D3. And then here, this distance, let's call this D2, it's equal to 3 feet. So we have those 6 forces applied on this object, okay? As you see, those 6 forces, would they have any resultant force? No, because they are just a set of 3 couples, right? 2 forces that is equal and opposite, so the resultant is 0. And then another 2 forces that are equal and opposite in direction, so 0. And then a third 2 forces, okay? So the resultant forces is 0, but they have a moment, okay? Those forces have the ability to rotate this object, okay? They are a couple, okay? That's what we want to find in this problem. We're required to find the resultant couple moment of the 3 couples acting on the shown object. Okay? So now, each couple has a moment, right? Each one has a moment. I have 3 couples. So the couple of the 3, the moment of the 3 couples is the summation of each one. Okay? Just sum the 3 together, that's the resultant moment. Okay? So now I can easily find the magnitude, okay, of each of those couples. Okay? But the direction, is it positive or negative? So let's first find the magnitude of each one of those, okay? And then let's see the direction, okay? So for the solution here, I'm not going to give signs because signs determine the, the direction. So the moment here, M, is equal to the summation of the moments, okay? Of each couple. So the first one, we have F1. We said the magnitude and the direction, right? Sorry, the magnitude. What's the magnitude? It's the magnitude of the force times D. D is the separating distance between the 2 forces, perpendicular to the direction of the forces, right? So F1, I should multiply F1 by, where's the 2 forces F1? This is 1, okay. This is F1, this is F1. What's the distance perpendicular to those 2 forces? 4. D1, 4. So it's simply F1 times D1. What about the 2 forces F2?
3.
So I have to multiply F2 by D2, the 3 feet. And then F3. Those are F3. What's the distance perpendicular to their line of action?
5 feet.
D3, the 5. So let's write the numbers now. F1 is 200 pounds times D1, which is 4 feet. So let me write this, the units, pound, and this is 4 feet. F2 is 450 pounds times 3 feet. F3 is 300 pounds times the distance, which is 5 feet. Okay? while leaving those spaces, the signs of each one of them, okay? So now, for the sign. The sign determines or depends on the direction, right? The sign can be positive or negative depending on the direction. So all those moments, what's the plane or the axis where they act along? Z. All of them are MZ, okay? So actually it's this axis here. So to call this moment positive or negative, how can I determine would I call the moment positive or negative? The right hand rule. Okay? So I just direct the thumb along the positive Z axis, okay? And then the rest of the fingers will show you the positive direction. So actually, this is the positive direction. Okay? Rotating this object in a counterclockwise direction. Usually it's counterclockwise, okay? That is positive. So now, let's see each of those couples. F1. Is it rotating clockwise or counterclockwise? Clockwise.
Clockwise.
Right?
Yeah.
Clockwise, right?
Yeah.
Imagine this object, you're doing it like this. You're rotating it clockwise. So it's negative.
Negative.
So this one here is negative. Let's see, F2. We're putting those two forces on the object. Sorry.
Counterclockwise.
Counterclockwise. So those are positive. What about F3? So negative,
Clockwise.
positive. F3. Clockwise. Okay? You're rotating it clockwise. So that's positive as well. So now the moment is so this is clockwise, right?
Yeah.
Clockwise is negative.
Negative.
So the summation is negative 950. What's the unit?
Pound.
Pound feet. Okay? That's the units. That's the answer. That's what you were looking for. Just one step. What? Ask me. Don't ask him.
We're summing, right?
Yes, just sum them up. So this is negative 800. This is negative 1500. And then this is like 1350. Yes?
If by chance on the exam we stay consistent but happen to specify positivity and negativity in the opposite direction, would it be okay?
No, you have to follow the right hand rule.
Right hand rule, so always counter positive, always
Yes.
negative. Okay.
Good. Yeah. Okay? Any question? So as you see, it's so simple, this one, okay? Two-dimensional problem, and so easy, so simple. Let's see another problem here. Another easy one as well. Example 411. So in example 411, okay? We have a gear here. I'm not going to be able to draw the entire gear here. So you have a gear. Okay, that's a very, very bad circle. Let me see here if I can. Okay, so we have a gear here. Okay, and this is the two axes. It's a two-dimensional problem as well. Okay, and then there are two forces applied on this gear. A force like this F that is equal to 600 newtons, and at this point here there is a force that is equal and opposite in direction, 600 newtons as well. Okay, the diameter here, or the radius of this gear is 0.2 meters. Okay, as you see here, we have two forces, okay, that are equal in magnitude and opposite in direction, okay, and separated by a certain distance. Okay, if you extend this force here, there is a perpendicular distance. Okay, so there is a couple here. This is a couple, okay, and this couple is applying a moment on this gear. Okay, so how much is the moment? Is this moment about point O here, about the origin? It's about any point. Okay, so we would like here, you're required to find the magnitude. In the book, it asks you for the magnitude and the direction. The direction is what? Perpendicular to that plane, right? A couple, the direction is always perpendicular to the plane that is containing the two forces. So so we know the direction, okay? So we're required to find the magnitude of the couple moment acting on the shown gear. The angle here is given. This angle is 30 degrees. Okay? So now, how can we find the moment here? To find the moment, you need to find this distance. To multiply this F by this distance, right? The perpendicular distance. But as you see here, it's not straightforward. You're not given that distance right away, okay? So you have to use some trig, okay, to find how much is this distance, okay? It might be tough, okay? So instead of trying to find this distance, I will use another concept, okay, to make my life easy. If you can use trig, okay, and definitely you can use trig to find this distance, okay, this green distance over here. But if you find that difficult, and it is difficult, okay, you can think of another alternative. So what's the other alternative that I'm going to think of now, okay, is I would like to find the moment, okay, of this couple. Can I resolve this couple into other two components that is easier to find the moment? Let's see this. Okay, so this is how I'm thinking to solve this problem. This is not the only solution, okay? But this is, an easier solution to the problem, okay? So I'm just going to copy this here. So instead of finding this distance, this green distance, so instead of finding this distance, which I don't have, I will try to resolve this force into two components, right? Do you know how much are those components, a vertical and horizontal component of this force?
Yes.
Yes.
How much are those components?
600
600
sine.
multiplied by cosine 30 and 1 multiplied by sine 30. The vertical one is multiplied by cosine 30 or sine 30?
Sine.
Sine 30 here. And the horizontal one is 600 cosine 30. And the same for this one. This is 600, okay, cosine 30, and this one is 600 sine 30. So instead of having this inclined force, now I have the two components of it, okay? So how many couples do I have now?
4.
A couple is a set of two forces. How many two forces that are equal in magnitude and opposite in direction? I have two couples. A couple, this is a couple, two equal and opposite forces, two equal and opposite horizontal forces, and two equal and opposite vertical forces. What did I gain from doing this? The distance used with each of those couples is easy now to use, right? How much is the distance for each of those couples now?
0.2.
0.2, the radius of the gear, okay? So that's easier now. So here, try to resolve the inclined force into two components in the x and y directions, and find the moment of the new two couples. We don't have one couple now, we have two couples. Okay? So the moment is, we have 600 cosine 30 multiplied by the distance, which is 0.2 meters. This force is in Newton. And we have 600 sine 30 newtons multiplied by 0.2 meters as well. The direction, okay? Which is positive and which is negative. So this one, you're doing like this.
Positive. Positive.
Positive. It's counterclockwise, so that's positive.
Negative.
This one,
Clockwise.
clockwise, so this is negative. So now the summing those two, this is going to be 43.9 Newton meter. It's positive, that means it's counterclockwise. That's the answer here. Any question? Okay. So now let's see the third example here. So simple one. All three examples are simple. It's a three-dimensional problem, but it's so easy, okay? Let's see the problem here. You have let's throw the coordinate system first. So you have the z, the y, and the x, okay? And then you have a pipe or a rod, okay, that goes like this. First oriented with the y-axis, and then here it goes in the xz plane, but there is an angle here. So this angle here is 30 degrees. This is in the XZ plane, okay? This is point O, this is point A, this is point B. And then there are two forces. Let's throw them in purple here, that are in the z direction. The two forces are in the z direction, acting a lot at point A and point B. Okay? They are equal 25 pounds each. Equal and opposite, so it's a couple. Okay? So the distances here. let's throw the distances. So this distance is 8 inches. Okay? And then this distance here along this line parallel to the x-axis, okay? It's 6 inches. I'm sorry, the length of that pipe is 6 inches. The length of this part is 6 inches. Okay? And that's it. Okay? What do we need to find here? Okay? Is the couple of that moment. Okay? So find the couple moment, the moment of that couple, okay, acting on the pipe shown, and the information we have here, segment AB is directed 30 degrees below the XY plane. Solution here. How to solve this problem? Those two forces, 25 and negative 25, they both are in the XZ plane, right? So the moment, the resultant moment, will be along the Y direction. Yes?
Is the pipe fixed at the origin?
Okay, so we don't care here. Is it fixed or not? We're asking about the moment of the couple, okay? If it's fixed, then this moment will not be able to rotate it because of the fixation. If it's not fixed, then this moment will make it rotate, okay? This is not our answer here, okay? We really don't care about whether it's fixed or not, okay? We really care it's fixed or not, okay, later on. If it's a statics problem, okay, then definitely there should be a fixation here, okay, to prevent it from rotating, either under the application of that couple moment, okay? But if it's a dynamics problem, maybe it's not fixed, okay? But this is not our question here. We just want to find the moment, okay? The magnitude of the moment will not depend whether it's fixed or not, okay? Everyone understand this point here? It's a very good question, okay? So now, simply, now, to find this, I can use either scalar quantities, okay? Or I can use Cartesian vector notation, okay? So if I use scalar quantities, let's say here, use scalar quantities. I know the direction. It's about the Y direction, right? This moment is about the Y axis, okay? So first, the two forces, the two 25-pound forces are in the XZ plane. Therefore, the couple moment is in the Y direction. It's a moment about the Y, okay? The Y axis. So I know the direction. What's about the magnitude? M, the magnitude of the moment, is equal to the force times d, the separating distance d. How much is the force? 25 pounds. What's the separating distance? The distance perpendicular to those forces. Okay? Is it the 6 inches? No, the 6 inches is not perpendicular to their lines of action. Okay? It's inclined. So now, I need to find this distance here that is perpendicular to their lines of action. How much is this distance, d? So let's draw this triangle here. This is the pipe. It's oriented by 30 degrees. The length of the pipe is 6 inches. This angle here is 90 degrees. How much is d? This is in 3D. This angle is 90 degrees. Okay? It's not an acute angle. Okay? It's 90 degrees. How much is d?
6 cosine 30.
6 cosine 30 degrees. So 6 cosine 30. So multiplied by 6 cosine 30. So this is 130 pound inch. Okay? Is it positive or negative? This moment. It's rotating this way. Okay? Is it positive or negative? Again, the right hand rule. This is the positive direction of the y-axis. So this, just put the thumb along the positive direction of the y-axis. The rest of the fingers will show you the positive direction of the moment. So this is the positive moment. Okay? Is it positive or negative? Negative. Okay? So definitely this is negative 130 pound inch. This is if you use scalar quantities. If I would like to use Cartesian vector notations, M is what? R cross product F. What R? What F? I have two forces here. One is going up, one is going down. How to write F as a vector? F as a vector. It has three components. A component in the x, component in the y, component in the z. How much is the component in the x? 0. How much is the component in the y? 0. How much is the component in the z? Negative or positive 25, because I have two equal and opposite forces. One is positive 25. Which one is positive 25? This one is negative 25. Okay? So it depends which one you want to use. So I will leave this to you. Which one do you want to use? Who wants to use this one? Raise your hand, okay? Who wants to use this one? Okay, so we're going to use this one. More students wanted to use this one, okay? So this one, is it positive or negative?
Negative.
Negative. So F is negative 25 pounds. But I'm writing it in a Cartesian vector. I should use Cartesian vector notation. So there is nothing called negative 25 and that's it.
K.
K. The component in the x is 0, the component in the j is 0. What about R? What's R? So now, you said I'm going to use this force. should be the distance from this force to the force that you said you're going to use. So this is R. Okay? I have to use this R. Okay? So R is RBA. So RBA, it's RB minus RA, right? RB. What's RB? The three components of point B, the coordinates of point B. X. How much is the X coordinate of point B? 6 cosine 30. I. What about the J component? 8. What about the K? 6 sine 30. Positive or negative? Negative. That's RB. Minus RA. The X component of RA. 0. The J component, the Y component, 8 inches. The Z component, 0. So let's do this subtraction. This one minus this one, so it's 6 cosine 30. 8J minus 8J, 0. 6 sine 30K minus 0K, so minus 6 sine 30K. That's R. So now we just want to find M. It is equal to R cross F. So this is I, J, K, and then the three components of R, which is 6 cosine 30, 0, minus 6 sine 30. The force we have 0, 0, negative 25. Okay? So now, to do this calculation, I will use this row. So I just have this negative 25, because this is 0 and this is 0. I have negative 25 multiplied by this co-matrix here. Okay? So I just cancel those. So I have I times 0, and then J times 6 cosine 30. So negative 25 times negative, this is negative 25, and then J times 6 cosine 30. Okay? So here we have, this is going to be negative 25 times J times 6 cosine 30. So it's negative 130 J. What does J mean? That this moment is about the y-axis, okay? It was so clear for us without, doing the calculation that this moment is about the j-axis, okay? So, any question here?
Direction vector RBA. Shouldn't it be RA minus RB? Or it doesn't matter?
You're using this force, right? So you're taking moment, if you use this force, so you take moment toward point B. So you take RBA from from this point to the loop. Okay? You see here?
Tail to head, head to tail. Is your subtraction from tail to head or head to tail?
Oh, okay. Yeah, I got your point.
Tail.
RBA is, sorry, yeah.
It's RM.
So this is, yeah.
Yes. There we go. Perfect.
Okay, thank you. That's correct. So negative, and this is positive. So this is negative, and this is positive. So here is going to be negative 25, and then, yes, this is negative J negative 6 cosine theta. Okay? It's negative 25. And then multiplied by this this times this, minus this times this. Okay? Any question here? So, thank you. This is... So let me try to put this so that you don't get confused. RA minus RB, and this is RA minus RB. Okay? Any question? So you can either use the Cartesian vector notation, okay? Or you can use the scalar quantities. You're going to end up having the same magnitude. Any question here? The same magnitude, the same direction. So now, let's move forward, okay? To the resultant of a system of forces, okay? If the forces are not acting at the same point, okay, then adding them together will give you the resultant force, but they also have a moment, okay? Each of those forces would have a moment about a point, okay? About a certain point. So how to do this? Let's take this step by step, okay? Let's say now, okay? If I have a force like this, F, okay? It's separated from this point O, okay? The question now, I just want you to answer this question. Can we move the force F from its point of action to point O? Can I just move it from its point to another point? Yes or no? Who thinks yes, you can move it? Who thinks no? You said yes, you can move it. Okay. So, to answer this question, yes or no, okay? If I move the force, would it have the same effect? Then I cannot move it, okay? So, if I move it, I'm changing the problem, okay? It's not up to me to move it, okay? If I move it, I'm changing. This is a new problem. You're not solving the problem given, okay?
But if you meant by like changing it to the other side, which is the O point, then it's not going to make any difference.
Why?
For
No,
me, out of the
it's
left
a...
side.
Okay, so let's see this, okay? No, I'm talking about moving it to point O, not to the left side of point O. And even moving it to the left side of point O is not equivalent, okay, to having it at this point, okay? So the thing is, we learned earlier that F has a line of action. You can move F along its line of action. That's fine, okay? But you cannot move it from its line of action. Why? Because moving it from point O here, okay, to answer this question here, F has a moment about point O, right? How much is that moment? Equal to F times this distance D, right? So it has a moment, it has an effect, it can rotate an object about point O, okay? If I move F to point O, how much is the moment of F about point O? 0. So moving it, I'm just throwing or neglecting or diminishing its ability to rotate an object about point O, which is not the real life, okay? Which is not the real thing. So I cannot do this, okay? So it has a moment about point O. Moving F to point O will diminish this moment, will make the moment equal to 0. Then it's wrong. Simply, it's a different problem. Okay? So now, what I want to do is, I want to move F. Okay? We cannot move it. It's a different problem. If you move it, then you're neglecting or you're removing its rotational effect. Okay? I want to move it. Why I'm insisting to move it? It might be easier to me. If I move it to that point, it will be easier for me, okay, to deal with it. Okay? Can I do this? We said no, but I still want to do it. But I want to do it in a correct way. Okay? Not just move it. Okay? I want to keep this rotational effect. Okay? So now, the problem that we had, okay, so let me write this. If I need to move F to point O, what can I do?
You take the moment from point A, the first, right?
Yeah, but we're going to do it in a, more systematic way, okay, to reach the point that you just reached then, okay? So we have F here at a distance D from point O, okay? Look, if you have some quantity, okay, 7, okay, and you want to do some operation in this number, 7, okay, you want to multiply it by something, okay, and let's say you want to multiply 7 by 14, okay, does anyone, or 15 or 16, let's say 16, does anyone know how much is 7 times 16? I don't know. I just memorized 7 to 12, okay? So the timetable till 12. I don't know anything beyond 12, okay? So instead of multiplying 7 by 16, okay, I will change this 7, okay? I want to multiply 7 by 16. I don't know how much is this, so I will change this 7. I will add 3 to it. But now if I add 3, it's 10, right? Why I did this? Because I know 10 times 16 is 160, right? But this is, when I say now the answer is 160, is that the correct answer that I was looking for? Definitely not. I multiplied 10 by 16, not 7 by 16. So I have to subtract 3. Right? So now I can say it's 10 times 16 minus 3 times 16. This is 160, and this is 48. And then now it's what? 112. Okay? So that's 7 by 16. Okay? The same thing that we want to do here. You see, I'm just going to use the same analogy here. Okay? This f, okay, I want to move it to point O, okay? So what I'm going to do, I'm going to have the same force that I have here, but I'm going to add a force here, and the force here. Adding 3 and negative 3. Right? I didn't add anything. Right? I added two forces, equal in magnitude and opposite in direction, applied at the same point. So how much did I put? 0. I didn't put anything. Okay? So this is equivalent to what? I'm going to break it into two parts. I'm going to have this alone, plus those two forces. Right? As you see, I reached what I was looking for. I moved F to point O now. Okay? But I added this to it. What's this? It's two forces equal in magnitude and opposite in direction. Rotate separated by distance d. This is equivalent to what? A couple. A moment couple. Okay? Equal to Fd. So what do I get from here? I'm just going to sum those again. I can move F to point D, but I have to add a couple moment that is equal to F multiplied by D. Okay? Now this is equivalent to what we had originally. F here away from point O. So I can move F to point O, but I have to add a couple moment. Okay? Equal to F times this distance D. So now I didn't change anything. Moving F from here to here and adding this moment, it's equivalent to the original. Okay? I didn't change the problem doing so. Okay? Those are two equivalent systems. Okay? Any problem here? So now, how would that be useful? There is now an important tool we're looking for. If I have a system of forces, okay, and moments applied on an object, okay, I have an object like this, okay, and there is a system of forces, a group of forces, F1, F2, F3, and so on, okay? There can be hundreds of forces. And some couple moments applied, okay? M1, M2, okay? And so on. I had some couples, I removed the couples, I put the moments, okay? I want to find the resultant of those, okay? So the resultant for those, for a system of forces F1, F2, and so on, and moments M1, M2, so on, the resultant about any point, or about some point O, I have a resultant force that is equal to the summation of those forces, and I have a resultant moment that is equal to the summation of R cross F plus the summation of the moments. Where did I get this from? Okay? Those forces, I want to find the resultant of them. So I just added them, right? But they have a moment effect, okay, about some point. So the moment effect, I just sum those moments, okay, those couple moments. This is what we have here. And then I have to add the moment, the ability of those forces to rotate the object about some point O, as if I'm moving those forces to point O, okay, as we did here. This is the moment ability of this force about point O. So I just have to find Fd, which is in vector notation Rf, right? The vector R cross the vector F. So that's the resultant moment about some point O, okay? This is about point O here. So this is the addition of those forces, okay? This is equivalent. If I have those forces, I can just remove all those forces, all those moments, and put just one single force, okay? That is equal to Fr, and one single moment, one single couple moment that is equal to this. Where is Fr at point O? Okay? Any question? Really? You understand what I said here? Okay? You understand what I said? Okay. So now, let's solve some problems. We have 4 problems to solve. So some 2D and some 3D problems that we are going to solve here about the resultant of a system of forces and couples. So example 414, we have, this is a 2D problem. We have an object that looks like this. This is point O. This distance is 0.1 meters. This distance is 0.1 meters. Okay? This object, there are some cables pulling on it. Okay? Let's throw this in green. I have a vertical cable here pulling this object down with a force of 4 kilonewtons. I have another cable here attached to this pulling this by a force of 5 kilonewtons. The direction of this force is 5, 4, 3, okay? And another force here pulling this object by 3 kilonewtons, and this angle here is 30 degrees. So I have those 3 forces applied on this object, okay? The dimensions, the distance from here to here, this is 0.2 meters. This is 0.3 meters. And this distance here is 0.2 meters. Okay? what do we want to do here? What are you required to do? As you see, this is an object, okay? And as you see here, this object, okay, has dimensions, okay, that are not negligible, okay? So it's not like the particle that we studied in chapter 3, okay? The forces are not concurrent, okay? They don't meet at a point here, okay? If the forces meet at the point on the object, then they just meet at that point. The resultant meet at that point where they meet together, okay? But now those three forces, they don't meet at the point, okay? They have the ability to rotate this object. So what I want to find now is the resultant. How much is the resultant of those three forces? The resultant as a force has the ability to move the object, okay, linearly, and the resultant as a moment, those forces, has the ability to rotate this object, right? So I would like to find the resultant moment. But when I talk about the moment, about what point? Okay? What's the ability to rotate this object about what point? So that's stated in the problem. So what we would like to find here is find the resultant of the applied forces as a force and moment about point O. Okay? That's what we want to do. What we're going to do here, simply what I want to do is replace those three forces by a single force applied at point O, but moving it to point O, I have to add a moment, right? The moment comes from R times cross F, okay? As we proved here. Moving force from point to point, there will be some moment for each one of them. That's what I want to do. I will move each one of those to point O, okay? And then add its moment, okay? So now for the solution. I'm going to start solving it, okay? So I'm just going to copy this. And put it here. So I have three forces, okay? The resultant force. What's the resultant force of those three forces? Their summations. Their summation is the resultant force. I just have to add them together. That's what they are equivalent to. That's what we learned earlier, okay? That's what we did. Now we just have the moment, okay? But the moment has nothing to do with this one. I just add them, that's the force, okay? So now, are those forces all in the same direction? No, they are in the same plane, but they are not in the same direction. So I have to find their components or write them in a Cartesian vector notation. Whatever you want. Either use Cartesian vector notation or just find the components in the x and y and add them, those together, okay? So what I'm going to do here, I'm going to just resolve each one of those into its components and use the components. So this 3 kilonewtons, I'm just going to resolve into two components. How much is the vertical component and how much is the horizontal component?
3
Cosine theta.
Vertical.
3
Sine.
So those are the two components. What about the 5 kilonewtons here? It has two components. How much is the horizontal component?
5 3 over 5.
5?
5 times 3 over 5.
5 times 3 over 5.
Yeah.
What about the vertical one?
5 times 4 over 5.
5 times 4 over 5. It's downward.
Yeah, it's down.
Yeah. So it's negative here. And the 4 kilonewtons, this 4 kilonewton, it's already in the y direction, right? So I can write this in Cartesian vector notation, or I can sum the components, okay? So here, if I sum the components, so I need to find FRX. How much is FRX, the resultant in the x direction?
3 cosine 30.
3 cosine 30 plus 5
5 times 3
times
over 5.
3/5. Anything else? No. So FRX is 5.598 kilonewtons to the right? What about the y component?
3 sine 30.
3 sine 30
On negative 5 times 4 over 5.
minus 4
Times.
which is equal to negative 6.5 kilonewtons. What does negative mean? It's downward. Okay? So this is downward. So now I can say that those forces is equivalent to a force of 5.598 kilonewton like this, and the force here that is equal to 6.5 kilonewton. That's the resultant of those forces. But they are not at point O. To move them at point O, I have to add a moment. Okay? How much is that moment? There is a moment here. MR. A resultant moment. What's MR?
The force.
It's the moment of each of those forces about point O. I just have to sum this together. Okay? So MR is just the summation of R cross S, if you're going to do it in Cartesian vector notation. Or you can use scalar quantities. Because now this is a two-dimensional problem, so the distances are going to be easy, okay? You don't need to use the Cartesian vector notation. And the moment, this is going to be a moment in the z direction. That's it. You're going to only have a moment in the z direction, okay? So now let's find this one by one. The moment about point O, okay, of each of those forces. For the 3 kilonewton, I need to multiply this 3 kilonewton by its distance to point O. That's tough, because I need an inclined distance. Or I can use its components, the moment of its components. So let's find the moment of the components of the 3 kilonewton about point O. Let's start with this component. 3 sine 30. Is it rotating clockwise or counterclockwise about point O? Counter, so it's negative. So it's positive. So here I have positive 3 sine 30 multiplied by its distance to point O. How much its distance to point O?
0.2.
0.2 meters. And then let's see the other component, the 3 cosine 30. It's rotating in what direction about point O?
Clockwise.
Clockwise. So it's positive. Sorry, negative. It's 3 cosine 30 multiplied by its distance, which is 0.1 meters. So this is the moment of F, the first force, okay? And then let's see the other force. This 4 kilonewtons. How much moment does it have about point O? 4 times this distance, 0.2, right? This is the ability of this force to rotate this object about point O. It's clockwise, so it's negative. So negative. 4 kilonewtons times 0.2 meters. And then the two components here. what's the moment of this component? Is it clockwise or counterclockwise? This one.
Clockwise.
Clockwise, so it's negative.
Negative.
5 times 4 over 5 multiplied by what distance? 0.5. So I have negative 5 times 4 over 5 multiplied by 0.5 meters. And then this force, what's its ability to rotate this object about point O? No, not 0. It's not passing through point O. There is a distance between this force and point O. It's 0.1. It's rotating it in what direction? Counterclockwise, so it's positive. 5 multiplied by 3/5 times 0.1 meters. That's the resultant moment, okay? It's equal to negative 2.46. What's the units?
Kilonewton.
Kilonewtons meter. It's in about what axis? Along the z-axis. Or you can call it, if you want, negative 2.46 K. If you use Cartesian vector notation, you would have reached the same result. Okay? Now, this is the resultant moment. So I have this MR. It's negative. So negative is clockwise. It's 2.46 kilonewton meter. And those two forces, I can find the resultant. How much is FR? I have two components, so the resultant is just square root of that, which is 8.58 kilonewtons. Okay? So all those three forces, I can remove those three forces and put the moment equal to 2.46 this way and the force like this. Those are the actions. Those three forces are equivalent to a force, a linear force in this direction at point O, and an ability to rotate about point O of that magnitude. Any question here? Yes?
What direction did you say the 5 3/5 times 0.1 was going?
5 3/5 about point O. As you see, it's a horizontal force. Okay? Going to the right. Okay? Just imagine this object here. When you apply force to the right, here, this side, what's its ability to rotate this object about point O? Would it rotate about in a clockwise direction or counterclockwise direction? Imagine, I'm just putting my finger here. This is the pivot point, okay? I'm pushing like this. How would this object rotate?
Counter.
It rotated like this. This is the object, okay? This is the pivot point, okay? And then I'm putting a horizontal force to the left. So it's rotating counterclockwise, okay?
So then,
Counterclockwise is positive.
so
Yes?
why is the 3 cosine 30 different if they're like going?
Because it's on the other side of point O. So, again, this is the object. I'm putting, this is point O. Now I'm pushing like this.
Okay.
Yeah?
Thanks.
Is it clear? Okay. Okay, so now let's see another problem. So here, also in this problem, to find the resultant, if you would like to find this angle theta, can you find how much is theta?
Maybe FRS.
Exactly, you can find theta. Theta is, you find inverse, the 5.598 divided by the 8.58. Okay? That's the angle theta of that force. So now let's move ahead to another example. About calculating the resultant of a system of forces and moments. Here we have, it's a three-dimensional problem. Let's draw the three axes. This is the x, y, and z axis. Okay? There is like a column, okay? That column looks like this. Okay? It's an I section. And then it's extruded along the Z. Okay, so that's the column extruded in this direction. And then there are some forces acting on it, okay, on this column or structure. This is point O here at the origin, at the center of the column, okay? And there are some forces. Let's draw the forces acting on this column. We have two forces and a moment, okay? The moment comes from a couple. There were two forces, okay? Equal and opposite in magnitude, separated by distance, so I just removed them and put the moment effect, okay? So let's see here what we have. We have a force. This is point C. Let me try to draw this in a better way. Okay, so this point is right in the middle, okay? This is point C here. And then here, this point is point B, okay? This direction, along this direction, CB, there is a force that is oriented with this line, CB, okay? Acting on the column. It's F2. It's equal to 300 newtons. Okay? So as you see, it's in the XY plane, okay? It's oriented with this line, CB. And then there is a force here at point C, a vertical force, F1, equal to 800 newtons, okay? And then there is a moment, okay, in this direction. About this axis. So here we have an M of 500 Newton meter. What's this? Can I draw a moment as a line? A moment is a rotation, right? This is the line that represents, like, the rotation is about this line. The rotation is about this line. So it's a moment like this. This is the moment. It's about this line. Okay? So it's not about the x or the z. Okay? It's about this line. Okay? The magnitude of the moment is 500 Newton meter. What's the direction of this line? It's given. Okay? This moment is in the zy plane. So the vertical distance parallel to the z is 3. The horizontal distance parallel to the y is 4, and this inclined distance is 5. That's the moment here. Okay? This is 90 degrees. So I have this system of 3 forces, or 2 forces and a moment applied on this column. Okay? Let's have some dimensions here. The height here, this column, is 1 meter. Okay? Height of the entire column is 1 meter. This distance here is 0.15 meters. Okay? And this distance here is 0.1 meters. Okay? Clear? Okay, so we have all the dimensions that we need here. We have those points, 3 forces applied, okay? And let's write the problem statement. What is required to be found here, okay? We are required to replace this system. Replace the system of shown forces by an equivalent force and couple moment acting at point O. Okay? Any question before we start solving? Okay. So now, to solve this problem, we have 2 forces and a moment. We would like to find the resultant about point O. Okay? So do you think should we use like components or use Cartesian vector notation?
The resultant of the moment and the forces.
Yeah. So I guess here, Cartesian vector notation will be much easier. Okay? So now, using Cartesian vector notation, let's write the things that we have using Cartesian notation. We have a force F1. We would like to write F1 using Cartesian notations, Cartesian vector notations. How to write F1? What's the component of F1 in the X? In the Y? In the Z? That's F1. Okay? What about F2? What's the X component?
2. 0.15.
Hmm.
Negative
300, yeah.
cosine of 1 over, or 0.1 or 0.15.
A little bit close, yes. Something close. Let's draw this section, okay? So that it would be more clear to you. That's the I-beam. This is point C. This is point B. And that's the force, okay? It's acting, okay, that's the force here. It's acting along this line, FCB, okay? It's 300 newtons, okay? This distance, how much is this distance? 0.15. And this distance is 0.1, okay? So now, F2 has two components. F2y and F2x. I need to find this angle theta, okay? So I need to find this length. How much is this length? Square root 0.1 square plus 0.15 square. Right? So now F2x is the horizontal component, that's 300 newtons times 0.1 divided by the square root of 0.15 squared plus 0.1 squared. F2y is the vertical component, so it's 300 newtons multiplied by 0.15 divided by square root 0.15 squared plus 0.1 squared. You agree with this?
Yeah.
Just the force cosine theta and sine theta. Instead of finding the cosine and the sine of the angle, I'm just using the, the distances, the horizontal and the vertical and the inclined distances. Okay? So now I can write F2 using Cartesian vector notation. How much is the component in the x?
X.
300 and 4 by 0.
X, it's... Okay, let me put this... Actually, we needed to rotate this, okay? This is C and this is B, okay? This, okay? This distance is along the y-axis, okay? So, this is F2, to be more clear, this is F2y, and this is F2x. Okay? To be oriented with this CD, okay? As you see here. So now, the force in the x, it's negative. As you see, this is the positive x-axis. It's going in the opposite way, right? So it's negative 300 multiplied by 0.15 divided by 0.15 squared plus 0.1 squared, square root of this, I. And then about the j, it's positive, this is the positive y-axis, so this is positive. (300) multiplied by 0.1 divided by the square root of 0.15 squared plus 0.1 squared. So F2 is negative 249.6 R plus 166.4 J in newtons. Okay? So now I have F1 in Cartesian vector notation, F2 in Cartesian vector notation. Let's write M. I had a moment here, right, of 500 Newton meters. I want to write it in Cartesian vector notation. How to write M in Cartesian vector notation? The magnitude multiplied by the direction vector. Right? How much is the magnitude of the moment? 500 Newton meters. The directions. It's in the ZY plane. So the x component is 0, right? So 0, I. How much is the component in the y? The y. 4 divided by 5. Okay? But it's negative. Okay? So negative 4 over 5. Theta z. 3 over 5. Okay? So doing those multiplications, it's negative 400 J plus 300 K Newton meter. So now this, all I did is just writing the three forces that was given in the problem, just putting them in Cartesian vector notation to use them to find the resultant.
Is it still easier than the scalar one?
Yes. Try to do it using scalar one, okay? Just try to do it at home, okay? And let me know tomorrow, is it easy or not, okay? So now, the resultant, the summation of those forces, how much is the resultant force? How much is the resultant force? Just the summation of the forces. Sum F1, the summation of F1 plus F2. The difficult part is done, okay? It was difficult a little bit, yeah, to write F2, okay, in Cartesian vector notation. But the rest was easy, okay? But now, right, getting them in Cartesian vector notation, now it's so easy. F1 plus F2. F1, it's negative 800K. That's F1. F2, negative 249.6I plus 166.4J. So how much is the summation? Just sum each component, the I components. Negative 249.6I. The J components. The K components. Newton. That's the answer. That's the equivalent force. Okay? This is the resultant force. Now, I would like to find the resultant moment about point O. Okay? How much is the resultant moment? What's the rule? If I use Cartesian vector notation, the moment of each force plus any moment couple that exists. Okay? So the summation of any moment couple plus the summation of the moment of each force. The moment couples that we have negative 400J plus 300K plus R cross F for each force that we have. Okay? Let's see here. I have two forces. So I have to do R cross F for each of those forces. Okay? I have F in Cartesian vector notation, right? I need now to find R. Okay? R. What's R? R is the distance from the point to the force. To any point along the line of action of the force. Okay? To any point along the line of action of the force. Whatever is easier for you. So for F1, the moment of F1 about point O. The distance from point O to any point along the line of action on point F, on that line. The line of action of point F passes through point O. So I can just say 0. Can I say this point? Yes. Point C is a point on the line of action of F1. You can put R as the coordinate of point C. But you're going to get the same result. You're going to get 0. Try it, you're going to get 0. Okay? So now we have 0 cross F. It was F1.
So I mean there's no position?
The position, I'm measuring the position from the point where I'm taking the moment about to any point on the line of action of the force. So this force passes through this point. So 0. I can measure it from here to here. I can measure it from here to here. It's not going to make any difference. You know why? Because F is, I wrote it as 800K, right? The position vector from here to here, it's what? It's 1K. 800K times 1K is 0. Because K cross K is 0, right? So whatever, any distance that you're going to put here, any point along the line of action of that force is going to be something K. Multiplied by the force, which is 800K, is 0. Right? We said cross product of K cross K is 0, right? Yeah. So any point is going to be 0. And then we have the moment of F2. How to find the moment of F2? R times F2. What's R? The position vector from point O to any point along the line of action of point O. I can have the position vector from O to B. That's what many students do, because they think that you have to multiply by the vector to the point where the load is applied. No, or the force is applied. Any point along the line of the force. Okay? So B or C, which is easier?
C, because it's too...
C, because it's going to have less components. Okay? So RC cross F2. So here we have negative 400 J plus 300 K plus 0 plus RC. How much is RC?
1 meter.
No, there's nothing called 1 meter.
1K.
1K, okay? I'm using vector notation. You have to write it in a vector notation. Cross F2. Where is F2? F2, which is negative 249.6 I plus 166.4 J. So here we have negative 400J plus 300K plus, how to do this multiplication? I, J, K, 0, 0, 1, negative 249.6, 166.4, 0. Right? The cross product of those two numbers, those two vectors. So simply, this is going to be equal to, this part is negative 400J plus 300K, and then this part is going to be equal to negative 166.4 I minus 249.6 J. So the summation is negative 166.4 I, and then negative 650 J, and then 300 K. That's the moment in Newton meters. Any question? Any question here? Okay, so we still have 3 minutes, okay? So I'm gonna finish today the lecture, and then on tomorrow, Thursday,